Anyway, last time we finished talking about population growth. We talked about short-term growth methods, and then we briefly discussed long-term growth methods. Of course, this isn't really a population growth class or a civics class or something like that, so I think what we've covered is sufficient for the purposes of this class. Now I'd like to kind of shift the conversation a little bit into the concept of water demand, right? We talked about population and population growth. Why do we need to know population? Because we want to know what the demand is. Last week, I think the first day of classes, we did talk a little bit about sources of water demand, right? We said, why do we need water? Well, obviously there's eating and drinking, but also we have hygiene, so cleaning ourselves, but also cleaning our cars, our houses, recreation, the beach, go to a water park, etc. Irrigation, agriculture. So we've talked about the different ways we may use water demand. Of course, if you thought population growth estimation is a very muddy field and it's kind of like you're not really sure if you have the right answer, you got to be very, very careful. The same applies to water demand. We can estimate things, we can try to come up with ideas of how much water will be required based on the population of a specific region. But of course, we need to understand that those are estimates. I think that goes without saying for everything in this class, right? Everything in this class is all about measurements and estimates. So never take a number and say this number is perfect, it is what it is. No, everything is at best an estimate. Hydrologists typically determine water usage or estimate water usage on a per capita per day basis. So we look at water and we see how much water is used per person each day. Normally the units for that are GPCD, which means gallons per capita per day. So 1 GPCD means 1 gallon used per each person on each day. You have a demand of 1 GPCD, and how many people are in this room? Let's say there are 30 students in this room, each with a demand of 1 GPCD. How many gallons of water are we going to use in one day? 30. We have 30 students in this room, each with a demand of 1 GPCD. How many gallons of water will we use in 3 days? 90. Okay, so we understand the concept of the units, right? It's a pretty simple unit concept. And that's what we're going to use typically to talk about water usage and water demand. Now, the way we estimate water demand has a lot to do with the range of our estimation. I'll give you a question. No, there's no right or wrong answer, so I just want to see what you think. Let's say we have 3 types of estimates. We can estimate the maximum daily demand in GPCD. So for every day, we can figure out what is the maximum demand for that day. Right? We can have different water demands at different times of day, right? We typically use more water when we're showering and less water when we're not, basically. Okay? I could also try to estimate the maximum hourly demand. So at every hour, what is the maximum demand? Or I could estimate the annual average demand. So in terms of maximum daily, maximum hourly, annual average daily, which means that for the entire year, right, we come up with an average for each day or for the day, right, and come up with that demand. Which one do you think is more helpful when it comes to designing water supply systems? Maximum daily, maximum hourly, annual average daily. And let me write these down. Which one do you think would be more helpful and more useful?
Max daily is going to be the safest. It's going to, if you attribute the maximum daily to every single day, then that's going to be the safest amount of water.
Okay, I like that. So why do you think that would be better than, let's say, maximum hourly?
Maximum hourly, you're taking each hour basis, and if 1 hour is lower than the other hour, then you don't cover it, you're losing water, I guess.
Okay, so that's a good point. Any other
What's the difference between max daily? Oh, no, right. I would say annual average daily.
You would say what?
I would say annual average.
Annual average daily, so what would you say?
Well, because you can have like a baseline of what people should use, and
Okay.
you can kind of allow like a water supply that's a little more conservative than what they should use.
Okay.
I would say max hourly, because usually you're gonna have some kind of storage system, and so you're gonna need to know like the most, whatever hour of the day has the most, you need to know that you have enough in your storage system for that hour, because you're gonna be continually pumping more water into your storage system.
Like
So
that.
if you have enough in your storage system for that hour, then you have enough to cover it, and then it catches up throughout the day with your pump that you pump into the storage system.
Good. We have 3 different answers. Everybody else, who do you think is the most correct?
I agree with hourly.
I was thinking early for the 2.
Okay, so I heard a daily somewhere and some hourlies. Okay, the answer is all 3. So all 3 are useful, and all 3 are used in the design of water supply systems. They're just used in different components of your design. For example, I'm designing a pump. I want to make sure that the pump can meet, right, the maximum load at any time, right, so that's necessary. In addition to that, I can't really design my entire system for, let's say, the maximum daily or the maximum hourly, mainly because the system will be over-designed. So think of it, let's think of it in terms of chlorine. We add chlorine to our water supply so that water is disinfected as it gets to our tap. And if we were to use only the maximum daily or the maximum hourly amount, we would add a certain amount of chlorine. But then what would happen if you open your tap water at, like 11 a.m. in the morning when everybody's at work? Nobody's really using water. If you're adding the same amount of chlorine that you would add when everyone's using water.
Oh, it's gonna be nasty.
You're just gonna have chlorine. You'll be drinking chlorine basically, right? So different parts of your design are gonna take advantage of different measurements and different estimates. Like I said, there's no right or wrong answers. Typically, it's a matter of designing, seeing if it works, or seeing if somebody else made it work, and then you applying that into your system. Different populations in different regions also have different, I would say, different tendencies to use water at certain times. So in some cases, some populations, it may be helpful to use maximum daily values. Other populations may be useful to use maximum hourly values. It really depends a lot on what it is you're studying. I know that you don't like that answer. You want me to give you an actual answer of what to use. But really the answer is you can use all of them. You just need to know how to use them. What I'd like to talk about today is a little bit about how we can determine or estimate some of these average demands. Maximum demand is typically estimated as a function of average demand. So typically we find what the average demand is, we apply a factor to that, and we call that the maximum. Of course, that has a lot to do with statistical analysis of measurements. So normally if we take measurements and we find that the maximum demand is usually 1.5 times the average, then that's our factor. So there's a lot of statistics involved. Sometimes, or some types of hydrologists will deal with that, others won't have to deal with that, they deal more with the actual design, but I kind of want to do a little bit of balance of both because I don't know what type of hydrologist you will be. And you will be a hydrologist, I can tell you. At the end of this class, you'll be like, you know what, structure sucks, I want to be a water resources engineer. So we'll look at the different components and then you can decide which one to use, especially for your project, okay? I want to talk a little bit about average daily demand or the annual average daily. Mainly because that is the safest one to estimate. There's a little bit less room for error, just like Jaden had said. So I do want to start with that one. So the annual average daily demand obviously varies throughout the year, right? It varies with season, winter, summer, fall, spring. It varies day to day, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and it even varies hour to hour, right? So obviously choosing your annual average value based on measurements takes a little bit of studying and a little bit of analysis. As water resources engineers, we don't really care about any one particular number, but we do care about the variation in numbers. So whether or not your annual average daily demand is taken using hourly data, or using daily data, or using seasonal data, or monthly data, the actual number doesn't really matter too much to us right now. What matters is what are the variations if you would have chosen daily instead of hourly. And of course, you need to understand what those variations are, and based on those variations, then you can determine whether or not your estimations are valid or not valid. Let me explain myself. You could, for example, estimate an annual average daily demand of, and I'm just gonna throw a random number, but you can estimate a number of 50. Okay, and you say, okay, 50 GPCD. That's actually not a good estimate, but you could estimate 50 GPCD. And you can say, okay, 50, I'm gonna design my system with 50. You can't really make the decision to design your system unless you figure out what would that number have been if you had used monthly data. And if you have used monthly data and the number was 52 instead of 50, the variation is actually not that bad. So I think you're safe enough to use your number and apply a safety factor, peak factor to it. But if the variation would have been, instead of 50, 100 GPCD, then in that case you can say, okay, there's actually a lot of variation between my temporal distribution, which means that I'm gonna have no choice but to study all possible temporal distributions and then decide which one to use. We typically wanna go conservative, right, like Jaden said. However, we're not made of money, so we can't always go fully conservative. We can't just look for a peak value and design everything towards that peak value. Hydrology can be a little bit annoying for a lot of us because of the statistical component of it, right? Because there's always like, this is what could happen, we're not really sure, right? We design stormwater collection systems based on, what could happen, but at any point, things could get even worse. Same thing happens with water demand. Same thing happens with sewage design. So as long as we can get past those frustrations a little bit and we can kind of understand that what we're doing are essentially estimates, and as long as we're okay with that dance between, I want to come up with a good estimate, I also want to come up with a reasonable, cost-efficient method, then as long as we can, I would say dance through that, we should be okay. When it comes to average or the annual average daily demand, we typically use data, but you don't always have data on hand. I'll give you an example. I'm doing a water supply system for a small city, and we were told that we should, or the client wants us to come up with a nice model, and they want us to essentially be able to have a model that's user-friendly so that the city employees can then come up and update it later with flows. In that model, before we turn it into the city that hired us, we're going to have to consider things like model instabilities, obviously some modeling mistakes which could happen, right? We could consider things like convergence issues, okay? However, we can't really do all that if we don't know what flows to use. But the city says, we want you to turn this in by September. This was last year, but by September of this year. But we actually won't have the flow data until August. So I have two options. I can say, well, if you don't have the flow data, I can't really model anything. I can't really start working on my model, and then I'm only going to have a month. That's not going to be enough time. Give the job to someone else. I could say that. But I'm poor. I need money. So instead what I do is I say, okay, let's do that. And in lieu of the flow data, right, since I don't have it, what I'm going to do is I'm going to look at similar sized cities, right, and estimate what could be the water demand, and then work with that on my model so that my model has some realistic looking flows that I can use to start to fix it basically and address its instabilities, stabilize my model. I haven't got my flow data yet. I will get it, I think, next week. So hopefully the actual flows are similar to the flows that I estimated. As hydrologists, you will do the same thing. Sometimes you are going to have to estimate data when you actually don't have measured data available, right? And it could be for a variety of reasons, right? Not all towns and cities have flow meters in their water supply systems, right? Not all towns and cities have detailed data repositories where you can just like find data on demand. Okay? And when that happens, you turn to statistics and you use statistics in order to estimate your values. For annual average daily demand, there's a very, very famous equation called the Goodrich equation, which is a very, very good estimate, right, for maximum usage. Not for average, but for maximum usage. So the Goodrich equation tells me that the percentage, right, of the annual average daily usage is equal to 180 divided by time in days to the 0.1. What that means is that I can input a time. Let's say that I want to determine how much water is going to be used in 6 hours, right? I can input 6 hours here, and the number that I'm going to get is essentially going to be the percentage of what the average daily usage is. Okay. This equation is very helpful, and I would say it's very useful. I saw it when I was in college, and I also saw it again when I graduated and started working. So it is definitely an equation that is used. Of course, you want to be careful. I've heard younger engineers say stuff like, oh, we can just figure that out with the Goodrich formula. And I think the wording there is a little bit, I don't know, it's a little bit incorrect. I would say we can estimate that with the Goodrich formula. We don't actually get real values, right? We just get estimates. Now this P is going to be a percentage, okay? Which means that the Goodrich formula really only helps us if we have a reasonable estimate of what the average use would be. And again, you can get that reasonable estimate with neighboring or similarly sized cities. The equation is valid from 2 hours all the way to 1 year. And by the way, sorry, T is time in days. I said hours earlier, it should be days. So the equation is valid from 2 hours, okay, all the way to 1 year. So 2 hours would be 2 out of 24 days, and 1 year would be 365 days. You want to be careful because this equation doesn't really account for firefighting needs. So that's a different thing, right? So typically results typically the results that we get from this equation are for water that people consume, not necessarily for firefighting needs, but it's okay. The maximum hourly usage, right, can be compared to the maximum daily usage here. So for example, if I want to figure out what the daily usage would be, okay, all I have to do is insert 1 day into this equation, and the daily usage is about 180% of the annual average use. So what this equation assumes, right, is that the maximum daily usage is about 180%. So that's like 1.8 times, right? 1.8 times what the average use would be. I'm not really going to give you too many problems to work with this equation. I do want to try out some examples from the textbook just so we can get used to them. But I want you to be a little careful here because we're looking at a lot of statistical equations and a lot of estimates. These are not equations that I would recommend that you just take a number and punch it in without actually knowing what you are punching in. So we're going to do an example from the book, and hopefully that will give us enough math practice for this equation. But other than that example, I guess related to this class, I would refrain from using it unless I tell you to. Okay? Because it is something that you want to be careful. I hate to sound lazy, but a lot of what we're going to learn does come with experience. So a lot of times we'll have 2 different methods, and I just won't be able to tell you or give you a list of reasons why this method is better than this one, unless it's definitive for one project. So for example, I have 2 methods. I can tell you which method would be best for one project. I can't really tell you which method would be best for all situations. And unfortunately, a lot of that comes with experience. My experience is mostly in the stormwater side. On the sewage side, I do have water supply experience as well, mostly in urban areas, some rural experience. But if you're working on a project that's completely outside my scope of experience, I just won't be able to tell you, right? Because I don't know what that would look like. I could read about it, but I would rather actually tell you stuff that I know about instead of just read about it. All right, let's try an example. This is from the textbook. Let's say that the average daily water usage in a city is about 150 gallons per capita per day. And I would like to know what the maximum hourly demand in that city would be. I'm gonna give you some additional data. We find from statistical analysis that the maximum hourly usage is about 1.5 times the maximum daily usage. That's what we found. So given that information, I would like to figure out what the maximum hourly demand is given an average daily usage of 150 gallons per capita per day. We don't have any data for this region, so we're gonna have to turn to some estimates. I would say let's go to the Goodrich formula to estimate. The Goodrich formula tells me the percentage, right, of the average daily, okay? So in this case, I write down my Goodrich formula. And I am looking for maximum hourly demand, and I know that hourly demand, or maximum hourly demand is 1.5 times the maximum daily demand. So if I want to find the maximum daily demand here, I can't find the hourly demand here because remember, this is only valid from 2 hours and up, right? It's not valid for less than 2 hours. So, but I can find the maximum daily demand. So then, what would I input here if time is in days? Okay. So what does this give me? 180. Okay. What this tells me is that the maximum daily use is 180%, right, of the annual average use. Okay. That means that the maximum daily use is going to be 180%, that's just 1.8, times the average daily use, which is 150 gallons per capita per day. Punch that into your calculator. That should give you a maximum daily use of 270 gallons per capita per day. And from our previous knowledge, we know that the maximum hourly use is about 150% of the maximum daily use. So that's 1.5 times my 270 gallons per capita per day. Punching that into your calculator would give you a maximum hourly use of 405 gallons per capita per day. Remember, this is gallons, that's volume. Person is just person. And then day is time. So this is actually a flow rate, right? It's volume per time, over time. Okay. We can't always design for the maximum hourly usage, like I said. Sometimes we want to design for the maximum daily usage, but we need to ensure that our systems can actually handle the maximum hourly usage, even though they're not supposed to handle it all the time.
So with the units on the maximum hourly usage, so that's saying that if 24 hours a day, the usage was the max, it would be 405 gallons per gallon per day, correct?
So it is a flow rate, right? It just means that throughout the day, right? If you look at each hour in the day, the maximum in each hour, or whatever the maximum hour was, is going to be 405 gallons per capita rate. Remember, that's not a volume, it's actually a flow rate. It's how much flow rate at one time is being used. How much flow at one time.
So at the maximum point in time in the hour, it would be flowing that rate.
Exactly.
Gotcha.
Correct. It's kind of tricky, right? Because you have two slightly different values, right? We have that the maximum hourly usage is definitely greater than the maximum daily usage. Because this looks at flow rate, right? Well, let me use this so the camera can see. This looks at flow rate, right, being used each hour. Whereas this takes the volume and says, what's the flow rate used each day? It's very, very, it is complicated. And you may ask yourselves, well, why can't we just always measure what the hourly usage is and then just work our way backwards from there? Because the hourly usage does seem to be the more conservative value. We can always work our way backwards. The reality is that we don't have the luxury, right, to measure flow rate every single hour. I mean, we're doing a sanitary system study, and we do have flow rates there, and we do get every hour a flow rate at different points in the city south of Atlanta. But we have to pay a lot for that value, for that information. Okay? And we're getting to a point where we're thinking, is it really worth it to pay that much for our design? Or can we just take what we already have, the data that we already collected, and then come up with a statistical model in order to continue working on our project? Right? Because, of course, we need to make decisions like that. In our case, I'll just give you a spoiler since it doesn't really matter, we're almost done with this. But in our case, we will have to keep paying for it, mainly because the whole going back to the office thing is changing up our flows significantly. So we can't just take the flows that we've been collecting since like June, July 2020 to today, and then use those to model our city. We actually have to keep collecting flows to figure out what that difference was. So, too bad for me, but it is part of the job. Okay? These are essentially, consumptive uses, stuff that you're going to get water from your tap and you're going to use it for some things. There are also fire demands. Fire demand is a pretty interesting thing to study. I've done some fire design for fire hydrants. It's a lot of fun. It's very simple. It kind of feels like you're doing a college project, so I do like that. It is very simple. But the reality is that we can't really play around with that with fire values. We need to be sure that we have what we need. And when it comes to fire demand, definitely it is best to be on the conservative side. Okay? Here's the thing with fire demand. In general, it's a small quantity of water. So if you look at all the water, all the volume of water that's distributed by a water supply system, only a very, very, very small percentage of that will actually be used to fight fires. Now, you may think, okay, that's fine. That means that it's not going to affect our design that much. However, even though it's a very, very small quantity, it has a ridiculously high flow rate because we need it and we need it now. So yes, it's a very, very small volume, but we need it at a very, very large flow rate. Fluid mechanics students, you know what volume and flow rate is, right? Go ahead.
So would you have to increase the pressure in the system to account for it?
The thing is that obviously you can't just increase the pressure at a certain time, right? You need to design for that pressure entirely, and that's correct. So you think of it this way, and I think you bring up a good point that I'd like to talk about. You have a building that's 10 stories high, right? Now, of course, you know that you're going to have to design so that your water pressure can reach all the 10 stories because you have tap. You have bathrooms on all 10 stories. Okay? That's good. You may remember, or you may recall from fluid mechanics that we have a hydrostatic pressure equation, and we know that pressure is just gamma H. So if you know the H, you multiply that by 62.4 if you're in English units, and then you figure out what the pressure is needed to take water all the way up to this point. Now there's a little bit more that you need to do. You need to consider energy losses, friction losses, all those things, and you do that with the energy equation, which we've already covered in fluids. However, as long as you can get water up to that point with a certain additional pressure, you should be fine. Here's the problem. When it comes to fire demand, you are going to have to get water up to this point, but you're going to have to get the water up to that point in larger volumes, much larger than what your tap water would be. Okay? Which means that the pressure that you need to design for is actually going to be larger than this one. Now I'm going to go back to your point. Here's a problem though. I designed for a really large pressure here, okay, so that I can actually convey the required flow rate up to the point I want. What happens if I go too high on my pressure? What happens to my plumbing system? It can burst, right? So I also need to make sure that my pressure actually does not overwhelm my plumbing system. Most cities don't have the luxury of having a separate water supply and firefighting system. They're all part of the same system. So we need to design our system in such a way that we provide the appropriate pressure without overwhelming the plumbing system of a building. When I was in college, we did this project for a class where we were given kind of like a neighborhood, and we had to do all these different designs, pressurized systems, tap water, firefighting water, all these different things. And I remember that one of the things that really got us when we're working in teams, one of the things that really got us on this project was trying to come up with a good design for firefighting system that wouldn't actually make your pipes burst. I gotta see that class, so I'm not gonna tell you what I did because I don't think I did it right. But the point is, it is complicated, right? There's a lot of moving around, there's a lot of dancing around that you have to do. Okay? So very, very good point about the pressure when it comes to fire demand. What parameters do you think we need to consider when we're estimating fire demand? So I want to estimate how much water I need and the rate of water that I need for my fire demand, for my firefighting. What do you think I need to take into consideration? What would you take into consideration if you're being asked that? I say Hector, right? Hector, I come to you and I say, Hector, my city needs you to determine how much flow rate needs to be provided for firefighting systems. What would you do? And you can ask me anything. Let's say you can ask me anything about the city. What would you ask me?
How old is the plumbing?
How old is the plumbing? Okay, I want to know the conditions of the plumbing system. Okay.
How many fires were there last year?
Okay, that's good. Historical data. Perfect. Historical data. Good. What else?
Tallest building.
Sorry?
Tallest building.
What's the tallest building? Okay, that's good.
How
And
long-
where, I would say. Not just what, but where.
And then, like, how long did the fires last?
How long did the fires last? That's good. I would say how long did the fires last and what dissipated them? Was it firefighting? Was it a combination of firefighting and precipitation? Oh, you know, good. Actually, everyone's answering for you. I want an answer from you. What else would you ask? It's okay. So we thought of some things, right? We thought about stuff like, well, historical data, right? We thought about the condition of the plumbing. We thought about the actual elevation of the tallest building. I have some. I put a little list of some that I would consider. And I think one important one, the first one that I would ask about is the structural use. Is your structure residential? Is it industrial? Is it something else? That's very important. Because if you have two fires, one is an office building, and this happens at 2 a.m. One is an empty office building, one is a house in a neighborhood where all the houses are very close together. Which one do you think would take priority? House, the residential. So residential always takes priority, okay? Which is good, right? Because our home insurances aren't actually that great. I had massive flooding at my house. My insurance was like, well, if it's an act of God, we can cover it. And I'm like, well, I'm a Christian, so I guess that works. And but then they determined that it wasn't really an act of God. The pipe was actually about to burst, and apparently the inspector didn't catch it, whatever. So it wasn't an act of God, even though there was a lot of coincidences that happened in order for my house to flood. But anyway, typically, and when it comes to insurance, office buildings are a little better. Also, office buildings don't really affect your livelihood, right? Typically, residential buildings will take priority because that is where families actually live. Office buildings are also more or less self-contained in that typically you have one building that could house many offices, but it's only one structure, whereas residential places have multiple structures interconnected. Okay? So residential will always take priority. Does anybody have sprinklers in their house? I guess if you live in an apartment, maybe you do, but does anybody have sprinklers in their house? Yeah. Unfortunately, my wife and I bought a house that has sprinklers. And I mean, I thought it was cool. It's like, okay, good, we're protected. But it turns out that we're actually we're subject to once a year drill and once a year inspection, which means that once a year an alarm is going to sound in our house late at night, and we actually have to go out. Or just like the reason I don't like living in apartments, that's one of them. And yeah. Anyway. Going back to that sprinkler conversation, do you think the presence of sprinklers would also affect the water demand for fire? It would, right? Because you need more water for a structure that doesn't have sprinklers compared to a similar structure that does have sprinklers. The good thing about sprinklers is that they act fast, right? The whole thing about firefighting is that you gotta get there fast, you gotta start fast, because the more it spreads, the harder it is to control. So when there's sprinklers, because they act fast, ideally you typically assume that you need less water to actually fight fire. Okay? There's a really interesting book called Introduction to Fire Dynamics. And I thought it was about like physics of fire, which I think is really cool, but it's actually about firefighting. And it's from a hydrology perspective. It's a really, really good book. If you're interested in all that, you can look at that. Finally, the third thing I would ask about is the types of structures that we have. Not just the usage of the structure, but the materials that are used to build the structure. Okay? Puerto Rico, everything is built out of concrete, so we're good. We have fires, but they're not that bad. Here, everything is built out of wood, right? Wood, yeah, wood drywall, and then some filler that's really highly flammable. Okay? So typically the type of structure is going to determine how much water demand you need. Structures that are more prone to burning will require a higher water demand. So you want to make sure that your pressure here at that system, or your demand at that, or your flow rate at that system, can actually meet that demand. And finally, within that type of structure, we also want to look at the layout of the structure. How much open space does the structure have? How many walls does the structure have? All that is going to affect the propagation of fire. You know that fire typically stays contained to a room, right? We have a fire, we close the room. Typically, the fire can spread to the entire room, and unless it starts to spread in other ways, typically it will stay mostly inside of here until somebody decides to open the door, and then right? Oxygen fuels it. If you cut the oxygen supply, we're good. So all those things are going to come into account. Now in this class, this is not a fire demand class, which means that I'm not going to give you equations or methods to determine fire demand. Instead, we're going to turn to tables. There's a lot of lookup tables that exist in codes, and each city will have their own code, which means that when you are designing for fire demand, you're going to have to figure out what city you're designing for and look at what their codes are. There are some international codes and national codes, there's a table in the book, I think it's table 1.2. Let me find that table and tell you what the name of that table is. It's called the 2012 International Fire Code. You can use that as a starting point, but just keep in mind that typically international and national codes are usually the bare minimum. Normally cities may have higher standards. So be careful, okay? You can use them, but always look at what your city is going to require from you. Remember that the person that hires you and that gives you the data for you to work with typically is not the engineer that knows what it is you're doing, but the person that reviews your work does know what it is you're doing. So the person that hires you may tell you, oh yeah, you can use the International Fire Code. But then the person that's reviewing your work may tell you, no, we have a stricter code, okay? So always keep that in mind, okay? We talked a bit about these water demands, and we're gonna learn a little bit more as we work on the workshop. I would like to talk about, let me turn off this light. I would like to talk a bit now about precipitation, because this Thursday, we're gonna start our workshop on precipitation. And I think that before we start the workshop, it would be good to know a little bit of the theory behind it. Oops, here, write that correctly. By the way, just a gentle reminder that this is probably the only week that the workshop and the lecture actually align. In other weeks, we'll be covering different things on the lecture and the workshop. Last week, we talked about the different forms of precipitation, right? We said rainfall, snow, hail, and all these other forms of precipitation, right? Good. Typically, a water supply comes in two forms, surface water and groundwater, which we also discussed last week. Precipitation is what supplies the surface water and groundwater. So of course, if we want to understand water demand and water supply, we need to understand what precipitation is going to be like. If anybody plans to to live and work in, I would say any state south of Virginia, I would say maybe south of South Carolina, you're good because precipitation really only comes in the form of rain, sometimes hail, but the amount, and sometimes snow, but the amount is so small that it's almost negligible in terms of design. But if you live in the north, then you actually have to consider different forms of precipitation, not just rainfall, in order to make your designs. Okay. When we study hydrology, and I'm going to go back into fluids now. When we study hydrology, it's going to be very helpful to use a control volume approach to actually study our systems and our regions. Does anybody remember what a control volume was?
The volume doesn't change, or yeah, the space doesn't change, but what comes in and out can.
Okay, good. Wow, you must have had a good fluids professor. Who'd you take it with?
Oh gosh, what was his name? He looked a lot like you.
Good. So yeah, control volume is that you study a region in space, and what comes in, what goes out can change, right? But that region remains the same. And that's how we're going to study our regions. We're going to study them by treating them like control volumes. In other words, we're going to have our region, and in the future we'll learn that this region is called a watershed, but don't worry about that for now. We're going to have our region, and we are going to have some influx of flow. Where do you think this influx comes from? You study, let's say you're studying a region, let's say you're studying Marietta. Where does the influx of water come from?
Rain.
Rain. Good. We have rain. Within the region, rain can take many forms. Surface water, groundwater, we can capture it, we can move it around, we can use it, but it comes to us as rain. The Chattahoochee River passes through a lot of states. One of those states is Sandy Springs. Now, we typically don't use the Chattahoochee, at least that section of the Chattahoochee for water supply, but let's just say we did for a second. In that case, we would have an influx from rain, but also another influx from the Chattahoochee River, which collects rain that falls outside of the region and brings it into our region. Okay, so there are different sources of influx and flow and inflow. But the important thing is that if we study our control volume, we can say, well, water can come in, which means that it increases our supply in the region, and then water leaves. It leaves to the city, it leaves to the houses, it leaves to the people that are using them, it leaves for many reasons, okay? And of course, if we look at this in the form of a control volume, we know that as long as the influx is greater than our outflux, we won't have any water needs, right? We'll be able to meet our demands. All right, so if Q in is greater than Q out, we won't have any needs, we'd be okay. If Q in is smaller than Q out, we have problems, right? We're gonna have a need of water. In order to study how much water is actually in a region, we're gonna have to apply the continuity equation. You may recall this with a little bit of fear, but this was the continuity equation that we studied in class. What that equation told us is that essentially what comes in must come out, and if it doesn't, that means that the density of the fluid is changing. Now, this is a hydrology class, which means that we're going to take this continuity equation and we're going to apply it to water. Josh, I'm going to have to use you again. When it comes to water, which is a liquid, what can we say about the density of liquids? Or specifically about its change, the change in density in liquids?
That for the most part it does not change.
Exactly, right? When we're dealing with liquids, normally, unless we're looking at massive temperature changes, our densities will not change. So if my density doesn't change, then what's the derivative with respect to time if it doesn't change? Zero. Good. Also, if my density doesn't change, then I can take it out, right? It's a constant. I can take it out of this divergence. And then I end up with this nice little simplified form of the continuity equation. I feel like right now I'm only teaching for my students just based on your eyes and expressions. Yes?
What does the upside down triangle mean?
It's a Nabla operator. So it's a gradient operator. It just gives you the derivative with respect to all spatial dimensions. Now here's a good part for all of you. We won't have to deal with the equation in this way in this class. We're actually going to keep simplifying it until we get to something a little bit easier. Okay? Sorry, Josh. I know this is all like easy stuff for you, but let's let's simplify it a little bit more, okay? Can you remind me your name? California?
Kyria.
Hialeah? From California.
Yeah.
Okay, good. Yeah, all this tells me is that the derivative of u with respect to x, you don't have to write this, I'm just gonna show you the derivatives are equal to 0. And what we can get from this, right, and that's the important part, what we can get from this is that if the density doesn't change, and these derivatives, well, don't really change because my volume doesn't change, then all we can do is we can simplify this expression into a form that tells me that the flow rate in, right, minus the flow rate out will equal whatever the change in volume in our system is. If you're curious how we got from here to here, I'm just going to say watch the 1-hour lecture I gave on this for the fluids class, because I don't think we have time to redo fluids here. But the important part that we need to know is that if there's a difference in flow rate in and flow rate out, then the volume will change. And this actually should make sense to you conceptually. Think of it this way. You have a cup of water, or maybe a bottle of water. You punch a hole in the bottom, you have water coming out, but you're also pouring water into the bottle, right? If the rate at which you pour water is greater than the rate at which water comes out, what's going to happen to water in the bottle? It's going to fill up, right? But if the rate at which water comes out is greater than the rate at which water comes in, what happens to the water in the bottle? It drains. Good, good. And that's exactly what this equation is telling us. It's a very simple concept with overly complicated math behind it. Okay? A very, very simple concept. This expression can be simplified even further, right, into a form that we call the water balance equation. So, this dV over dt, we can just call it a change in storage with respect to a change in time. In hydrology, the S will almost always stand for storage. So when I say change in volume, really I mean the change in stored water with respect to time. And the sources of Q in and Q out can be many. Okay? So we are going to have to study some of these different sources. So if we're looking at a particular, I would say, if we're looking at a particular region, any region, it can be a city, it can be urban, let's just say it's a big region that covers urban, rural, mountains, just covers everything, okay? And we want to apply this continuity equation to that region. What are some sources of flow coming into that region? You already said precipitation, right? Precipitation, water comes into my region. Good. What are other ways water can come into your region?
Flooding.
But flooding isn't that part of precipitation?
But your rivers and stuff that flow from outside of your region.
Exactly. Good. Inflow. Okay. Okay, we're gonna call that inflow. So typically this is QSI. So typically we call this surface water inflow. Okay. Good. Any other ideas? We have inflow from surface water, so water that can come from a river into our region.
Transportation.
Sorry?
Transportation. Transporting water into your region.
Okay. So we do have water that can be, oh, you mean like human transportation. Okay, that's a really good point. I don't know what the variable will be for that, because normally most water balance equations don't include it. But you do bring a good point. When you have places with drought, you have to actually bring water from other regions. So we can call it whatever you want. I'll just call it QT. But, you know, it's just not in the water balance equation. Good. Any other sources of inflow? We said that water can come in through rivers. In addition to surface water, what other types of water did we have?
Groundwater.
Okay, so we can actually have water come into our region on the ground, right? Good. So we have groundwater inflow into our region. I think those are good sources. Precipitation, surface water inflow, groundwater inflow, and then water that is transported into our region. What do you think are sources of outflow? So that was inflow. Now let's look at outflow.
Evaporation.
Can you say it again?
Evaporation.
Evaporation, good.
Residential.
And let me say, let's call this surface water evaporation. Okay. Yeah, can you say that again? Somebody said something.
Residential.
Okay, so usage, right? Just water that we use. And again, we can call this U for usage, we can call it whatever. These variables, every single book has different variables. So don't take these as this is the variable, okay? Really what matters is the concept, not the letters themselves. But anyway, usage. Any other source, we have evaporation, water can evaporate, or we can use water, okay? Any other?
You have outflow of surface water and groundwater too.
Exactly, so we have outflow, so we can call it O, outflow of surface, or actually QSO, I think. Yeah, surface outflow, good. Is water on the surface the only way it can leave our region?
Groundwater.
Groundwater, good. Groundwater outflow, I heard something I liked from over there. Infiltration, good. Water can infiltrate as well, leaving our region by just joining the groundwater, okay? Good, infiltration. We're missing one. What are other ways that water can leave our region and go back into the atmosphere? We said that?
We say the plant one?
Yeah.
Yeah.
Transpiration, good. Evapotranspiration, good. Awesome. So here's the thing. We started with this very complicated continuity equation, a nice nonlinear differential equation that we can solve. And now we're going to simplify it into a nice arithmetic equation where all we have to do is add and subtract things. Right? Conceptually speaking, what are we saying? Conceptually speaking, we're saying that the change in storage, and let's multiply everything with respect to time. So I can just say change in storage is going to be equal to the precipitation plus the surface water inflow plus the transported water plus groundwater inflow minus evaporated water minus used water minus surface water outflow, surface water outflow minus groundwater outflow minus, I use comma instead of minus, infiltration minus transpiration. Again, these are not variables in the mathematical sense. We're talking about concepts here. That's all we're doing. We're talking about the concept of precipitation that adds to storage or removes storage. If you ever want to use this and actually add numbers to it, then of course you need to make sure that your units match. Right now the units don't match here because I would have to add delta T to every single one of these. It's just a little bit too much. So in terms of concepts, if we understand how much water is coming in, how much water is leaving, then we will know how our storage changes. If we know how our storage changes, then we know the state of our water supply system. That's called the water balance equation. What time does this class end? 1:30? Okay, so we have enough time. Let's go to example 2.1. It's a very simple water balance equation. And it's going to force us to deal with units as well. That's why I like this example. All right, reading from the book. At a particular time, the storage in a river reach, a reach is just a section of a river, that's all it is. So the storage in a river is 55.3 acre feet. And this is something really interesting. You always want to keep in mind that hydrologists, we are notorious for coming up with our own units that just benefit ourselves. So the storage is going to be 55.3 acre feet. What is this, dimensionally speaking, in terms of dimensions? What is this? Is this an area or a volume?
Volume.
It's a volume, right? Because we have area multiplied by length, it's a volume. Of course, we could convert it into cubic feet. What?
Why?
Because
Why? No, I'm saying why acre feet? Why not just do feet cubed?
I'll explain. So typically, you have big areas for regions, which are typically measured in acres, right? 1 acre, 43560 square feet for a given depth. But then you want to measure that in terms of depth as well. So normally the acre stands for your entire area, and then your depth is just whatever. When we talk about rainfall, sometimes I talk about in inches acre, right? So I say, well, for every acre, there was however many inches of water rainfall. So it's just a way to kind of help us talk about things. But yeah, acre feet. And like I said, I like this problem. It's going to force you to deal with these units, okay?
Is that a US standard thing, or is it like the cubic meter
Um,
on the other side of the wall?
so acre is part of the US customary system. Feet is part of the US customary system. You could see it as a combined unit of the US customary system, but it's not a standard unit. The standard unit for volume will be feet cubed. So yeah. If you work in other countries, you'll have your own things to deal with, right? So in Puerto Rico, we have the cuerda, which is it's not an acre, but it's close to an acre. So we use that for areas, but then we use acres for hydrology. So it's it's a little bit complicated. Virgin Islands is another place where it's all like messed up, right? Because we all use metric units, English units, kind of mixed up. Make sure you use English units for this, but metric units for that. Speak in metric, write in English, or vice versa. It's crazy. Anyway, at that point, let's say that the inflow into the reach is going to be 375 cubic feet per second. CFS stands for cubic feet per second. And you'll see people write it as CFS. It's very, very common, okay? You're gonna see that all the time. So get used to that one. And we'll say that at that same instant, the outflow is 563 cubic feet per second. Okay, that's at one instant. Let's call this state number 1. At some instant in state number 2, 2 hours later, so we can call this time 0, and we can say this time 2 hours later. At some point, the inflow and outflow are 600 for inflow, and the outflow is 675. I would like to know what the storage is at that point. So I'd like to know how much the storage changed and what the storage is. There are obviously problems with how much data was given, which means that we're going to have to come up with some assumptions to work with that. But let's see if you can figure those out before I tell you what they are. So how would we solve this? First of all, storage is volume, but then we're given inflow and outflow in volume over time, which is flow rate. Okay, how do we know how much storage is being added?
You need to convert the cubic feet.
We can do that. We can convert to cubic feet just to make things easier for us. Okay, we can do that. So Jaden says let's convert to cubic feet. So our storage, I'm going to call it storage at state 1, is going to be 55.3 acre feet. There are 43,560 square feet in an acre. And if you work in hydrology, you're going to memorize that number really quickly because you're going to use it all the time. So I can say there are 43,560 feet squared per acre. How many cubic feet of storage do we have?
2,424,088,000. No, it was 2.4 million.
2.4 million? 2.49 million?
Yeah, I didn't put commas in here, so I don't know.
Somebody tell me the storage.
2,408,868.
All right, 2.49 million, right?
41.
41.
That's why you don't use cubic feet.
Yep, I hope that answered your question, Seth. Good. Awesome. So what does this tell us right now? Just let's look at state number 1 at time 0. What do we know about the storage in that river at that time?
It's decreasing
Why is it decreasing?
because our out is way bigger than our in.
Exactly, right? We have more water leaving our system than we have entering our system. What about state number 2? What do we know about state number 2?
It's not decreasing as much though.
It's decreasing, maybe not as much. Would you expect your storage at time 2 hours to be lower than the storage at time 0 then? Okay. Now we have a problem here. We only have two measurements. Inflow and outflow at 0, inflow and outflow at 2 hours. We don't know what happens in between. So what assumptions can we take? Could we assume that the inflow and outflow is going to be this for the entire 2 hours and then right at 2 hours switches to this? Is that a good assumption? Why not?
That would make
I believe you. I just want to know why. Why isn't it a good assumption?
Realistically, it doesn't really happen, right?
Okay, yeah, not very realistic. Okay, could we assume that for the first hour, this is my inflow and outflow, and then for the second hour, this is my inflow and outflow? It just changes drastically like that? Not very realistic either, right? Any ideas on what we could assume?
So it's linear.
Okay, we could assume that the inflow changes, right, increases linearly to 600 CFS, and at the same time, the outflow increases linearly to 675. That's an okay assumption. And for this case, unless we have any statistical data to use, it's the best assumption. Okay? We could have better assumptions if we had more data that could point us towards that trend. But right now, we don't. So we do know how this flow rate changes. We know that inflow increases linearly from 375 to 600 CFS over the course of 2 hours. We know that outflow increases linearly from 563 to 670. I don't know why they couldn't just use round numbers. But anyway, 563 to 675 linearly over the course of 2 hours. Can we find, using just that information, can we find the change in storage? Knowing how the inflow changes and knowing what the initial storage was.
Yes.
Yeah, we can. Yeah, let's figure that out. So there are two ways we can solve this. We can integrate, right? We can just come up with a nice equation for inflow, which is just a linear equation, and just integrate that over the course of 2 hours and get the total storage volume that's added. We do the same thing for outflow and get the total storage that's removed, and then we just add everything up. That's one way to solve this. A second way to solve this is to say, and maybe geometrically is a better way to look at it, but we can say, this is my inflow, and I'm going to plot it here. This is time, and this is Q in. We start at 375. We increase linearly over the course of 2 hours to 600. What happens if I integrate flow rate, the flow rate curve right now? What does that give me?
Did you change
In?
storage?
Yeah, right? Because flow rate is volume over time. You integrate that, right? That gives you volume. I think we understand how integrals work here, right? Good. If we don't, I'm giving a math course next week during my office hours and cover all those things. So that means that the area under this curve, this trapezoid, gives me the amount of storage that is added to my system. Can we agree on that? Given that information, can we find that area under the trapezoid? Yeah. Okay, let's find it. What's the area of a trapezoid? It's the average of the two heights, right? Multiplied by the base. All right, let's figure that out.
$975, right?
Sorry?
It's $975, right?
All right. Yeah. And what units does this give me then? All right. Let's look at units. What are the units of this flow rate?
CFS.
CFS. What's that? Cubic feet per second, right?
We're multiplying it times.
What are the units of time?
Oh.
Okay. So what is our storage really? Once we fix the units. Nash, 4 classes with me. I'm disappointed in you. But it's okay.
Well, you didn't write units on your graph, so technically.
Oh yeah, try to blame me, huh? You gotta play it that way. The book also does this, but then the book takes a nice approach. It writes the units as CFS times hour, which,
That's totally right.
yeah, give me the storage, okay?
Is it 3.51 times 10 raised to 6?
Okay, thank you. 3.51 times 10 to the 6th. Like that? All right, can somebody confirm?
That's what I got.
Perfect, good. So we found the storage in. Now we can go ahead and find the storage out. The outflow starts at 563. Let me write the units so Nash doesn't complain. And it increases to 675. And that is over the course of 2 hours. The area under this curve is going to give me the total volume that leaves my system.
.46.
4.4 what?
46.
Thank you. Times 10 to the 6th?
Yeah.
Thank you. Somebody confirm that value, please?
Yeah.
That's right.
Perfect. Finally, we go to our final question. What is the storage at 2 hours? Conceptually speaking, what would I write here? Not the numbers, but the concept. What would this be? We get the storage at 2 hours?
SL, 2 hours minus.
The main storage minus.
See the main storage
Okay,
minus
main storage, okay.
plus Q in minus Q out.
Q
Q.
or
Oh,
delta?
I'm sorry, yeah, that.
Okay. Minus delta S out. Good. You punch those numbers in, and you should get your total storage. And just to make this just give you a little bit of extra work, give me that storage in acre feet so that we can check with the book. So get your number, divide by 43,560.
33.5.
Perfect. Can somebody confirm that value?
Yeah, I would have rounded up, but yeah.
6. Okay. Good. Any questions? See, we need to sometimes come up with different ways to solve this. I mean, I think graphically it works best for me because I love geometry. If you don't love geometry, you could have just integrated that and you would have landed at the same answer, okay? Because integrating is just finding the area under the curve. The book solves the same problem with a different process, so you can also look at the book's process. What the book does is just average everything. Could also work, but only when there's linear relationships. So that's why I didn't want to use it in class, because it will not apply to every single scenario. Any other questions with the topic of water balance? Oh, sorry, go ahead.
How do we go from the 975 to the 3.51?
I'm sorry. Oh, how do we go from this to this? It's units. So we got this 975 by taking this area, which has dimensions of CFS and hours, which means it's 975 cubic feet per second times hour. So all we do, right, to go from here to here is look at how many seconds are in 2 hours, basically. So that we can have cubic feet divided by second, multiplied by second, so the seconds cancel out. If this answer is correct, how many seconds in an hour? 3,600, right?
Yeah.
Okay, so if this answer is correct, then if you take 975 and multiply that by 3,600 times 2, you should get this number as well. Because all we're doing is converting units. I see everyone packing up, but we have 2 minutes left. Not sure why we think that we're going to finish class 2 minutes early. Before I let you go, I do want to talk a little bit more about precipitation because we will start on Thursday. We will get to do some work on Thursday. I do want you to get ready for it a little bit. So when it comes to precipitation, I'm not gonna write anything, let's just discuss. When it comes to precipitation, we can't estimate or calculate it with any certainty, right? All meteorological models are very, they're estimates. We can think of the percentage of rainfall, we can't really say it's gonna rain definitively, okay? So when it comes to precipitation, we typically rely a lot on measured data. As hydrologists, as water resource engineers, we're gonna rely a lot on measured precipitation data. Does anybody have any idea how precipitation is measured?
Inches per hour?
Yeah, the units, but like how?
Oh.
Usually the collecting it.
Yeah, you collect it, right? You collect and you figure out how much it rained in a certain amount of time, okay? So let's keep that in mind, because we're gonna use data, but just because data was collected at one site doesn't mean that I'm gonna design right there. Maybe I'm designing a structure here, even though the nearest rainfall collection was half a mile away. And then I have to come up with a decision to make, like, how can I estimate or convert the measurements that I got half a mile away to the measurements that I should get here? We don't have time or budget to collect rainfall every time we design a project. So we rely a lot on existing measurements, and we have to find methods to bring those measurements and apply them into our area. We're gonna talk about those methods on Thursday, so I'll see you then.
Right as I said.
Yeah.